My name is Tom Kaitchuck. I'm a distinguished engineer at Dell. And today I'm going to be talking about streaming video analysis in Rust using GStreamer and Pravega. Pravega is an open source project that I've been part of for a long time. And this is our experience using Rust. This isn't an introduction to Rust talk, but is just us sharing our experience and hopefully providing some lessons that will be useful to all of you. So let me define the problem we're trying to solve in this that brought us on this project first. Our goal was to build a streaming video service that could be deployed to a data center or to a customer, and they would be able to have many cameras going in to it and be able to do analysis on those videos in real time. So doing things like object detection, seeking, and have this all sort of scale up to large numbers of video streams and have good performance. An example of what that looks like is here's NVIDIA's Deep Stream running on a live video stream. So this is a generic object detector, and it is detecting that there are cars on this highway. This is a very sort of basic application, but you can imagine much more sophisticated ones being built on top of an architecture that supports this. To do this, we relied on an application called GStreamer, which is, it's been around for a very long time. It's a pipeline-based framework for chaining different processing elements related to video and audio processing together. It is most commonly, or it was originally and most commonly done for client-side sort of processing work. But this is now scaled up, so it's more generic and pluggable. And there's over 2,000 plugins for it. So this is sort of an ideal technology to build upon. So there have been several existing approaches that people have tried. The most obvious of which is sort of a batch architecture, right? Like you can imagine, you write one day's worth of video data into a file in S3, and then you perform analysis on it through some Hadoop job or something like that. It's a very common paradigm. The obvious trade-offs of that are latency and dealing with recovery in the case that your device that's writing that dies midway through. Sort of the traditional solution to that has been to look sort of smaller size batching. So this is the natural transition that people have had from moving to Hadoop to things like Spark, where you're going from large batch of a day to small batch of a minute. This still has a bit of latency, which may not be an issue for many applications. Like 1 minute of real time, within 1 minute of real time is probably acceptable to a lot of applications. But failure recovery is still complicated, especially if you're dealing with things pipelined and potentially out of order within that, right? But if you also think about it, it sort of messes with your data format. One thing that we actually saw customers doing was people were encoding video by grabbing every frame, re-encoding it as a JPEG, sending the JPEGs through a Kafka, and then extracting them out on the other side with a time window, reordering them into the appropriate time, and then re-encoding it as video. This is an awful lot of code, and it destroys your compression ratio, and it ruins what would otherwise be a nice format, and dramatically escalates storage costs, because Kafka is obviously going to be storing it on what need to be high performance drives, and we'd like to be storing months, if not years worth of data. So we want something that does better than this. And we want something that's just a truly streaming model from the beginning that treats recent and historical data as contiguous, and you can move between them just by reading it. So to do that, what we really want to do is we want to lean on an object store as our long-term persistence. We don't want to try and scale up and have local storage on all these nodes because, well, cloud storage is cheaper, right? And if you're only worried about archival data, that's what you want. But to do that through the same API is a little bit tricky. Similarly, we want to have easy recovery, to just have a point in time. Oh, you failed at this point. You can resume from that point. So the notion of atomic rights is very important. And to be able to declare an end to data, like I only want to retain data for 1 month, and have that data disappear after 1 month, while at the same time not screwing up your format. Like if you just set a retention policy on S3 and say, oh, I'll throw out all my data after 1 month. Well, your format better support that, or whatever you're using to do indexing better be aware of that. So we want something that sort of automates all of this. Fortunately, that exists already, and it's called Pravega. That is exactly the use case that Pravega is built for, and it does all of these things very well. The basic architecture is as follows. You're writing data in, it goes to Pravega, and read access goes through Pravega, whether it be real-time or batch, and Pravega is in the background interfacing with your long-term storage, whatever that may be, HDFS, a cloud store, whatever. And it's intermediating those calls, but providing a streaming interface and real-time access and atomic writes and all that good stuff. So you just operate on the abstraction of a stream. The other advantage that Pravega brings to the table is scalability. I need to explain this graph a bit. This is a test that we did just to demonstrate scalability in terms of number of writers. So here, the throughput is in 2 gigabits per second, which is very modest and something that all of Pravega, Kafka, Pulsar can easily handle from a single source. What we did is we scaled up the number of sources while holding the data rate, the total data rate the same. So when we go up to 10 writers, each of them is writing 1/10 as much data, and 100 writers, 1/100th as much data. So this is just demonstrating what happens when you scale up the number of sources independent of the actual data rate. And as you can see, Pulsar literally collapses, and Kafka is barely any better. It doesn't hold up to a large number of writers concurrently, whereas Pravega is only interested in your data rate. And if it supports it, then it can support it, and if not, not. So an end-to-end pipeline looks something like this. You have a camera that's producing some data. It's extracting into a video stream. Then you run some derivative algorithm on it. In this case, we're doing a NVIDIA GPU-based object detector who's outputting some JSON. And so we have a modified stream with bounding boxes. And then we have additional metadata that can be put off to the side for analysis with a Flink or a Spark application. Here is a demo of that. So here's, assuming this plays. Maybe. Unable to play video. Well, great. The whole point of pre-recording this demo was to prevent exactly that. Anyway, this is, if that played, it would be a live demo of this working through a web UI with multiple video streams, jumping back and forth between them, fast forwarding, rewinding, and showing object detector working and labeling things, and then piping that into a Flink job, which was allowing you to run queries against it with a SQL-like syntax to produce graphs showing how many cars go by on a highway. So we wrote this in Rust, and that's sort of an interesting decision, because why would we do that, right? There just weren't a lot of Rust users, and none of our customers were asking for Rust. That wasn't a priority. But we still think this makes sense, or at least I do. And I think this comes down to something that came up in a talk a while back by Brian Cantrell, and he talks about the idea of platform values, the idea that software and languages have certain values that they bring with them, and that people who use those software are going to be attracted to those values and build on those, and they will get stronger in those dimensions. Not every piece of software is going to have all of these values. These are just ones he identified. But not every piece of software is going to have all of them, because when push comes to shove, you can't, right? Certain ones are higher priority for different types of applications and different types of frameworks. And naturally, those applications and frameworks are going to prioritize what's important to them. So if you look at those, he sort of identified of these 10 that he considered Rust's values. But I would sort of group these into three sort of personas. There's this one we hear about with performance, safety, and security, but I think there's also a second and third one, this interoperability, integrity, and robustness, and then composability, extensibility, expressiveness, and rigor. And all of those you can sort of visualize differently. The usual approach that everyone talks about, and the one that gets the most attention, is this performance plus safety and security. And the reason I think that gets a lot of attention is because it's very hard to do in a lot of other languages. So this is a graphic that came from the Google Android team, where they're talking about like where do you have security exploits? It's when you have unsafe code that's not sandboxed and running on an untrustworthy input. But sometimes you can't change the fact that your input is untrustworthy, and you don't want to have a sandbox for performance reasons, and so that leaves you in a tight spot where you may want, for those same performance reasons that you don't want to put a sandbox on there, to not use your C++, but there aren't a lot of options that have extremely high performance if you really care about getting every last ounce of power out of your CPU. And this has been repeated many times. For example, Amazon's Firecracker, which is the KVM that underpins AWS, Google's virtual networking infrastructure that they run in their cloud to provide each user with their own virtual network. The Facebook cryptocurrency, Diem, Rust TLS is a cleanroom TLS implementation. Similarly, Trust DNS, full end-to-end DNS stack. Tor, the anonymous web browsing agent. 1Password has their stack implemented in Rust for this reason. Servo was a classic one that is a Chrome renderer that would, they wanted to have it be higher performance and add multi-threading, but couldn't do it in C++ because the overhead, the security risk of running something that's as complex as CSS and rendering it in C++ was a problem. And since they did that, Chrome and Microsoft Edge have also rewritten their CSS renderers in Rust. TIKV is very much the same story, and Wasmer is also a very interesting one that mirrors the CSS story, where here you're wanting to execute WebAssembly. So you have a full-blown language and you want to containerize it, but you don't want to have a very high performance cost because everything is going to be, it's going to execute on every single CPU instruction. So those are all great use cases, and if you find yourself in that boat, by all means, Rust is an excellent choice. But that just wasn't our choice. That wasn't our problem. Our problem was much more basic than that. We didn't have a performance issue because we were going to be network bound anyway. We didn't have a security extreme concern because, well, we're dealing with trusted code on both sides of the wire. Our problem is that we were dealing with a stateful client. And to understand why, you need to think about recovery, which is if you imagine you have a client that connects to a server, it sends data, the server can track where the client is. And when the connection goes away, it can tell the client, oh, you left off after that point, and it can resume and resend the same data. But this means that the client code can't be code-genned. It can't be just automatically generated from a template or something. And as soon as you say that you're going to have a client with state that you're going to manually write, well, it makes sense to start offloading a lot of other things to the client as opposed to putting them on the server because you can do things more effectively and efficiently. And by the way, your CPU usage isn't centralized. So what we ended up with was a client design that looked like this, where we're implementing a core client implementation once, and then we're writing bindings for each of multiple different languages that connect to it so that we can interact with that same client library so that we don't have to write the client logic over and over again. So this is basically doing what's called FFI, foreign function interfaces. And there, a different set of values matter, which is the second set of Rust's personas, where you're concerned about interoperability, integrity, and robustness. And understand why. FFI can be fairly complicated. You need to think about things like calling conventions, alignment. Is the memory garbage collected in one or both languages? Can the objects that are returned contain references to each other? And when is the data freed? Is there a particular allocator that's used? What about error handling? Are there other restrictions on threading? For example, Python has a global interpreter lock that you need to hold before you execute any code in Python. There are OS-specific requirements in languages like Go, for example. And character encoding. Oftentimes, different languages have very opinionated views on what a string looks like that may differ from one language to another. And so aligning these on a cross-language basis is not necessarily as straightforward as it seems. And I think this is an area where Rust really shines. And to understand why, I think it's important to look at a method signature. If you look at C, here we have a fairly generic method. It's just write, and it's writing some bytes. But what's going on here? We have two parameters that must agree with one another, and if they don't, it's a bug, right? So that's already like one sort of oddness. And then we're encoding an error in a number in the return value. Go improves on this a bit. Well, wait, and memory management, of course, is just through documentation because you don't know whether the caller or the callee is supposed to free that buffer. Go improves on this a bit by including the length into the parameter, so those are unified. Having a separate error value, so it's not encoded into the normal return value, that's useful. And the memory management is done by garbage collection, which is certainly better than relying on documentation and human effort, but can be difficult to work with on a cross-language basis. If you've ever tried to get the Go and Python garbage collectors to cooperate with one another when handing objects back and forth between them, you'll understand why. Compare this to Rust, where Rust has errors that can't be ignored, unlike by accident, unlike the Go code there. It has compile time memory management, which is an interesting way to do it because it's not garbage collected, but it's also not manual in the way that C is. It has very explicit contracts. For example, here this first parameter, it's dictating that this is safe to pass between threads and can be invoked concurrently for multiple threads. And here, it's very explicit about what the semantics of the buff are, that it won't be modified, that it will not be retained or any pointers retained to it after the call returns, and it is the responsibility of the caller to free the buffer. This is amazing and exactly what you want when you're dealing with cross-functional language, because you can put, or cross-language functions, because you can put the specifications that you want into the method signature very explicitly and have them enforced. In fact, this is so ideal that people have automated it. Here's three frameworks. This is PYO3, which automates calling from Python, Neon, which does the same thing for Node.js, and Helix, which does the same thing for Ruby. An example of what this looks like in your code is if you wanted to call a function from Python, you can annotate the function py function and import PYO3, and that function will be callable from within Python with no extra work on your behalf. So it really is a dramatic improvement in terms of the ability to operate on a cross-language basis. And this is made possible by the explicitness of the function signatures in the language. So what lessons did we learn when we were doing all of this? The first that's very interesting, I think, is thinking about ownership. Ownership is a very central concept to Rust, but doesn't appear explicitly in any other language. But I would argue that it is in other languages, and that it is implicitly in most other languages. So here I've written some Java on the slide here, and there's two alternative methods here for process foos that process them in different ways. The first step in both of them is to sort the list of them. And this is done in two different ways. In one case, it's put into a tree set, which is a sorted collection, and by adding it to it, it will implicitly sort them. And the second is by calling sort, a standard library function, on the list itself. Now, these differ in ownership. And this concept exists in Java because these are semantically different in the following way. If you were to, inside of the first function there, grab an element from that the sorted set, and then modify it in such a way that its comparison changed with respect to other elements, this would violate the invariants of treeset. It would render the internal ability of the data structure to function. It would just cause assertion errors or any number of other problems inside of treeset, and you wouldn't be able to predict accurately what it's going to do. Because there's an implicit contract on treeset, which is that when you pass items into it, that the collection now owns them. And similarly, in the process foos example, the collections.sort method is not owning the data that's passed into it. The assumption is that the caller retains ownership. And so if the implementation of collections.sort were to be modified in such a way that it, for example, handed the list off to another thread and then in the background called sort concurrently, that would break the invariance of the caller. And in both cases, if you weren't aware of any change that would alter the implicit assumptions about ownership of the function signature or go against them, would result in an error on one side or the other. So this concept really does permeate. The next interesting thing that we encountered was that Rust just doesn't need the visitor pattern. It's all over the place in our Java code. And to understand, like, consider when you're doing request reply, it's very straightforward because you end up with a bunch of different types and you have something that has an interface and you say, okay, well now I need to process these. But your processing code is almost certainly type specific. So you end up writing something like this where you have this reply processor and then each of your possible replies, you have a method that is a one-liner that just calls an overloaded method on the object that was passed into it. So this is definitely not ideal, but it is what you sort of live with in Java and C#. Rust has something which is perhaps boring to everyone in the functional programming crowd, but is absolutely amazing for somebody coming from Java, which is that it has enums where the individual elements of the enums have member variables that are specific to them, just like an object. And this is just amazingly better because you can replace hello with the hello implementation up on the upper right with the hello reply, and any fields that it has can be simply fields in the enum. And this allows you to replace this mess with something much more straightforward, which is just a match statement. The other thing I want to throw out there, not because it's Rust specific, but because it's just such a great pattern, and I really want to see everyone do it everywhere, which is the notion of using the type system to enforce invariants. So here's a great example, right? Instead of having like a user and a Boolean on it, like whether or not the user is authenticated, we really want to have authentication be something that's validated, right? And so the good way to do that is to embed it into the type system by separating a user and an authenticated user into separate objects, and then using visibility rules to have the one and only one way to create that user to be the authenticated user to call authenticate, passing in a user. Another example of the exact same thing would be to do it with request and authorized request. But this pattern is a great way to ensure a happens before relationship that you can type into a method signature, because you can say, oh, this method takes an authorized request. Rust definitely goes beyond this, though, and you can use this same sort of pattern where you're leveraging the type system to enforce additional invariants. This is a good example of one. Here we have a connection pool, and it has a get connection method, unsurprisingly. But this connection object has this interesting parameter at the end. The syntax is a little obscure, but what this is doing is it's saying that this connection cannot outlive the pool that it came from. By definition, the connection must be closed before the pool is closed. You can't close the pool first and then the connection in it be left alive and then potentially error or whatever would happen otherwise. So this prevents that sort of runtime consideration from even having to be brought up because the situation is ruled out at compile time. Another way this can be done is with ampersand mute. The classic thing that this is able to do is to use for exclusivity, but we found it very effective as a way to impose ordering requirements or ordering semantics. So here's an example where we have a writer object that takes a self as a mute. So when that is invoked, that write method, by definition, is ordered with respect to all other calls to that write method. So in the case where we want to impose ordering semantics of, say, writing to a stream, we can say, okay, well, the writes on the stream go in the order of the write invocation, which is by definition defined because this method signature mandated that it was semantically defined. So yeah, this can really be leveraged. One of the classic problems we face is one that exists in basically any application that's like managing connections and multiple requests concurrently, which is you end up with this notion where you say, okay, I want to have multiple requests going over the wire, and I want to have like multiple things coming back over the wire. So you end up with this situation where you have some sort of state about like what's going on that is being accessed from both sides, from both the top and below, from replies coming back from the server and from data coming down from above. And this gets very messy very quickly. It's a little bit hard to deal with, so much so that people have built patterns around it. The classic example is actor frameworks, where you have a reactor pattern, where you have a queue in front of it, you have an actor who's running in an event loop and that gets a state and an update and then applies that update and does a transition. And that's a much easier model to deal with, except it has the problem that you have to buy into a framework and you have to code to a specific specification, and it really has a way of intruding on your code, in addition to introducing runtime overhead. What we discovered we could do with Rust, which was sort of remarkable, is that you can do what I would call the async reactor pattern, where you replace the queue with an async rendezvous queue, the channel with an async rendezvous channel. Rendezvous channel is a channel essentially with zero capacity, where you're handing off directly from one thread to another. Now, with async await, the way it works in Rust is that the futures aren't real. They aren't like a completable future in Java or C#. They are sort of done in the background via a polling mechanism. So when you wait on a future, it's actually transferring. It's as though the actual physical thread is being switched to another one. So an async rendezvous channel does nothing. It's essentially a stack switch behind the scenes. It looks like you're working with two distinct threads, but there aren't two distinct threads. It's just two distinct code paths. And if you combine that with a state, which is just an enum, you can write essentially an actor framework in about 12 lines of code. And this is all just normal code out of the box, nothing fancy. You don't need a framework, and there's no overhead, right? You can just do your async block, have a loop, pull on your channel, and then decide what you want to do based on the state in the channel. And this has defined ordering semantics, so you get all the niceties that you would with an actor framework, except there's no queue, so there's no overhead associated with it. There's no state transition or locks or anything else. And because Rust futures are zero cost, this all compiles away into nothing. It's as though you wrote the perfectly optimal, like handle every possible state code, except you didn't have to write it that way. So it's a very neat pattern. But we came to love, that we didn't choose Rust for, but really came to appreciate later, was this third persona that I outlined, which is this composability, extensibility, expressiveness, and rigor. What that resulted in is a lot of libraries and crates that were published that are just really great. They have very clear APIs. They're very explicit about exactly what they expect and how you can interoperate with them, and how you can extend them, and how you can work with them. And they're extremely well defined, and they're by virtue of having such a clear definition, have been very carefully crafted to do what they say extremely well. And so we were just like, whereas in virtually every other language I've worked in, adding a dependency was like horrible and avoided at all costs, because you're like, well, maybe I'll just write it myself because I don't want to take on this other thing and be worried about it. That just isn't the case in Rust, and we had great experience with our dependencies. First and foremost of these is SERDI. SERDI is by far the best serialization framework I've ever worked with in any language. You define your object just as you normally would, and you put two annotations on it, serialize and deserialize, and it does the rest. It can support all of those formats, and it does so out of the box and generates the code you need on demand with no separate compilation step. And best of all, you can define your own format, which is what we did. We wrote our own format, and there was no code that was per object per format at all, which is absolutely wonderful. You can just define what it means to write an integer to the wire, and SERDI takes care of the rest. I wish every language would emulate this, because it's such a great experience. Here are some other tools we found super useful. Feel free to snapshot this. I would absolutely endorse every single one of these crates. They were really useful, and I have nothing but positive things to say about them. Clippy, Rust format, and docs are all built in, and I would I would strongly encourage everyone to run them as pre-submit checks because they just do everything exactly what you want. Tracing is a great way to get logging and things automatically inserted into logs, snafu for error handling, etc. Yeah, can't say enough about how great Rust libraries are. So what we really came to love at the end was also the borrow checker, which is the thing that everyone says you're going to hate and that you're sort of geared up to fight with. But it did something that I expected, which was that we no longer had to think about thread safety. When we were writing in Java, we spent 20 to 30% of our design time thinking about how do we design this to be absolutely sure it's thread safe and that we won't ever have any errors, and we have to, how do we structure our components such that we can easily validate that it is correct at code review time. And so that's a huge time sink, and you spend a lot of time focusing on it and thinking about it. And I was really looking forward to working in Rust where we just wouldn't have to think about it. But what I didn't anticipate was not only would it save us that time, but it would change the way that we wrote code. Because when you no longer have to worry about that, suddenly the things that you contorted your design around to try and make sure that it was provably correct or that you could convince a human that it was correct just weren't there anymore because you could lean on the compiler to do that enforcement. And that allowed you to do designs that you just wouldn't in other languages because you had more freedom and you had more power to sort of leverage some other aspect that you were concerned about to make that better. So with all of Rust personas, I think they're sort of about one thing. There's sort of three different ones, but I think at the end of the day, they're all really about empowerment. And that's why I love it. Thank you. So let me see if I understand the question. The question was, how do we manage the data in a distributed way such that we're trading off chunk size versus latency?
Well, at the beginning, you said that was a common problem.
Yes. Okay. So normally, suppose you had an object store and you were writing to it sort of naively and directly, right? It won't let you read back the data that until you're finished writing it. So if you're writing, data for an hour into a single file, then your latency is by definition at least an hour. Pravega doesn't have that issue. You can write to Pravega and then read the data within a single-digit milliseconds. And have a live feed directly off of Pravega. In the meantime, Pravega is going to batch that up into a very large object and put it into your object store. But just because it didn't arrive in your object store doesn't mean you can't read it. And it's still durable as soon as Pravega acts it, which is within, again, single-digit milliseconds. So Pravega is able to do that, in very, very fine-grained, individual writes, which are guaranteed to be atomic. And then as soon as they're acknowledged back, the writer can forget about them. So the writer's buffer is only a couple megabytes. And it's just, that's the writer's buffer for the case of, failures or something went wrong with the connection or whatever. But in general, if everything's sort of up and running fine, the end-to-end latency will be very low because it's going to be read by the reader before it's actually hitting the object store.